All right, hello everybody. Welcome to 6.2. We're going to talk about Cartesian product of sets. All right. So kind of we're going to see this first example. I'll actually come back to it later, but it says for a rally, there are four cars, Swift, Indica, Santro, Alto, along with other vehicles. These cars need to be coded. How many different pairs of codes can be generated by using three codes, H, M, and T? To answer this question, you need to know the concept of Cartesian product of sets. All right. So, like I said, we will come back. We will discuss this question later on. But for now, let's get a look at what Cartesian product even means. So let A and B be any two non-empty sets. And the Cartesian product of A and B is a set of ordered pairs such that A times B, I suppose you could say that, is the set A and B, where A is elements of A and B is elements of B. So basically, long story short, let's say we have a set. When I say a set, you can just think of, you know, it's a collection, right? So let's say set A has 3, 9, 12. Like those three numbers make up that set. Those are the numbers that are in A. Let's say set B has like 2, 8, I don't know, 10, right? So the Cartesian product, what this is saying is that the um, Cartesian product is the set A times B, where it's going to be like, for example, it'd be 3 and 2 would be an ordered pair. 3 and 8 would be an ordered pair. 3 and 10 would be an ordered pair. So every element of A with each element of B, and it would continue like 9, 2 as an ordered pair, 9, 8, 9, 10, 12, 2, 12, 8, 12, 10. So it's basically we're saying this, we're just saying that each element of A will pair with each element of B. So each number in A or each letter, whatever is in A, will pair with each in B. That's essentially the English version of that definition. And this is just reminding you that ordered pairs are unique. So 2, 7, it's obviously not the same as 7, 2. All right. So let's get our first kind of example out of the way. Our first example says A is 1, 2, and B is the XY. Then write A times B. So A times B would be like this. Let's see here if we can make room. So we're going to use this little brackety thing because it's like that's how you write a set. But we're going to have each element of A. So for example, start with the 1, right? We're going to have 1, and then with the element of B, X. So 1X would be one of the ordered pairs. Then we'll have 1Y. Okay, so again, we're setting each element of A to each element of B. So 1 goes with the X, 1 goes with the Y. So 1 goes with each part of B. We also have to keep doing this for the 2 because 2 is also part of A. So 2 comma X and 2 comma Y as the ordered pairs as well. And that's going to be the end of that set. So each element of A paired with each element of B. It's really that simple. Okay, it's not really too much more complicated than that. Now we can observe that n, the number of elements of A times B, this is kind of interesting, is the number of elements in A times the number of elements in B. So what I'm saying here is that you'll notice that there are 2 elements in A and there are 2 elements in B. So the number of elements in them, 2 times 2 in this case, which is 4. That's how big the A times B set is. You're going to notice there are 4 elements in A times B. Now, granted, one ordered pair is a single element. One ordered pair is a single value in this set. So 1, 2, 3, 4, just like this tells us. So this is a rule of thumb. However many elements are in here and in here, if you multiply those amounts together, that's how many ordered pairs you should get. Okay, so like here on this one, you're going to see that here there's 2 elements here and 2 elements here. That means when I multiply a Cartesian product here, I'm gonna have four ordered pairs altogether because 2 elements times 2 elements would be 4. So you're gonna see I'll have 4 ordered pairs. So like this one would be 2 comma E, 2 comma B. That's 2 ordered pairs, and then 4 comma E and 4 comma B. And then don't forget to close that off. So I'm not really good at these brackets, but I try my best to draw these brackets. All right. But yeah, and again, you'll notice again it's 4 elements, which is good. All right. Now, if either or both sets A and B are what we call null sets. Oh, come on. Which basically means an empty set. So like it doesn't have anything in it. Then A times B is also a null set. So a null set, again, just as a reference, means empty set. So for example, it would be like if we had this last problem, if B was just equal to a blank set, like there's nothing in it, no A, no E, no B, just nothing in it. Well, then how would you multiply 2 with nothing, 4 with nothing? You can't have 2 in a blank and 4 in a blank. That's not how that works. So if this is empty, then there's nothing, there's no way to combine them, which is why it's saying that A times B is also a null set, meaning you can't do it. It would also be an empty set. It's basically like multiplying by 0. If you can't multiply by something, then you're not going to have anything there. Kind of like if you multiply by 0, you end up with 0. It's kind of the same philosophy. Now, if either or both sets A and B are infinite, then A times B is also infinite. Um, Kind of the same idea. Imagine that B was just an endless set. It never ended, right? Well, then you'd be here all day, forever, doing 2 times everything. And on top of that, you still have to 4 times everything. But again, if it never ends, then you would never stop doing that. So if one of these sets was infinite, like let's say B, if B was infinite, then our Cartesian product would also be infinite because I'd have to be multiplying it along forever. All right. In general, A times B is not equal to B times A. Why is that? Well, I mean, the main justification there is, of course, we mentioned it earlier. Let's say, for example, the set 1, 2 would not be equal to the set 2, 1, right? So I think we're gonna prove that next. Yeah, I was gonna use a previous example to explain it, but I guess we'll just prove it next. So we'll just go on to the next one. We'll prove why that is, right? This is then verify that this is the case. So we're gonna just prove here why A times B is not the same as B times A. All right. So let's start with A times B. Now notice you have 2 elements here and 1 element here. So 2 elements times 1 element means, well, 2 times 1 is 2. So we should have 2 ordered pairs here. Just an FYI. So we have 1 from A is going to pair with the 3 from B. And then we're going to have the 2 from A pairing with the 3 from B. And that's all the pairs, right? So again, there's your 2 elements that I was mentioning, right? Because if there are 2 elements here times 1 element here, 2 times 1 means you're going to have 2 ordered pairs there. 2 elements of this set. Now, what if we reversed it, right? What if we did B times A? See, the order here matters. Oops. So B times A would be taking 3, pairing it with the 1. So 3 comma 1. And then 3 paired with the 2. 3 comma 2. And are these the same values we had in this one? No, they are not, right? So that's just proving, right, that A times B is not the same as B times A. They just create different sets. All right, let's see it again. So this one is a 2 by a 2. So again, you should see 4 ordered pairs here. So let's start with A times B. A times B, we're going to have 4 with R. We're going to have 4 with T. Then we're going to have 7 with R. And then 7 with T. And there's your 4 elements. Looks good. Now, of course, if we reverse this, we try B times A. You'll see it's not exactly quite the same. B times A, we'd have R with 4. We'd have R with 7. T with 4, and T with 7. So as you can see, they are different ordered pairs. They're not the same thing. They're reversed, but that doesn't mean they're the same, right? Now, a nice little trivia question here is, would there be a case when A times B is equal to B times A? I'll give you a second to think about that. All right, so the answer there is yes. There is. Hopefully you've thought of it. Um, this would be if if A is equal to B. This would be the case. So like if I did 4, 7, times it by another 4, 7, right? If those two sets were identical, if A was the exact same set as B, then this would be true. So yeah, you can have it, but obviously only under really certain situations, certain circumstances. It's worth understanding. It just mentions that the number of elements of A times B is the same as the number of elements of B times A, as you can see that. A times B was 4, B times A was 4, right? Because either way, 2 times 2 is 4, no matter which way you put it around. So, yeah, same thing here. 2 times 1 versus 1 times 2. Both sets here, we're going to have 2 elements in them, 2 order pairs in them. Yeah, the number of pairs will be the same, but the ordered pairs themselves will be different, right? That's what we saw. Number of ordered pairs is the same. They both have 4, but the ordered pairs themselves are different. Unless, like we said, A is equal to B. That would be the only circumstance where they actually would be the same ordered pairs. All right. So we kind of see that a little bit on these. We have A times A, so we're gonna do A twice, right? So essentially we're gonna be doing 1 comma 3 by another, 1 comma 3. Just think of it that way, right? A times A. So we'll have should be 4 elements altogether because right there's 2 in here, 2 in there, so 2 and 2 makes 4. So we're gonna have it would be 1, 1, 1, 3, and then we'd have 3, 1, and 3, 3. That's perfect. And again, the number of elements in A times A is going to be 4 because the number of elements in A times the number of elements in A again. This was 2 elements times 2 elements, which is 4. And you can see that because we have the 4 order pairs. So just another reminder with that. All right. One more example of it. We'll do it again. So this one would be, 3, 7 times another 3, 7. So this would be 3, 3. 3, 7, and then 7, 3, and 7, 7. And again, the number of elements in A times A is equal to 4 again, right? As you can see, 4 ordered pairs. All right. And then one more for practice. This is probably something I'd let you guys do on your own in class, but just for the video, I'll go over it. So if you want to pause it, do it yourself real quick and then check, that'd be great. But yeah, I'll go ahead and answer it. So this one would be P, Q. I'm sorry, it would first be P, P, I guess. I don't know if the order really matters too much. Then P, Q, then Q, P, and Q, Q. All right. And the number of elements again is equal to 4. Now we have an ordered triplet. So this gets good. Um, so let's give this one a try, right? So it's the same thing, right? But we're going to do it 3 times instead of just twice. So essentially it's 1, 3 times another 1, 3 times another 1, 3. So A times A times A, we're going to have 1 with the 1 and the 1. So 1, 1, 1, an ordered triplet. We're going to have the 1 with the 1 with the 3. So 1, 1, 3, right? Then I'm going to have the 1 with the 3 with the 1. 1, 3, 1. And then we have the 1 with the 3 and the 3. 1, 3, 3. So again, it's every combination basically. It's what we're looking for, right? 1, 1, 1, 1, 1, 3, 1, 3, 1, 1, 3, 3, right? And we're still got to keep going because we got to do the same thing with the 3, right? We got to do 3, 1, 1, 3, 1, 3, 3, 3, 1, 3, 3, 3. So we'll have 4 more in total here. So 3 has to get paired with each combination as well. So 3, 1, 1, 3, 1, 3, 3, 3, 1, and finally 3, 3, 3. Ordered triplet. Now, it's interesting, again, number of elements of A times A times A. Well, remember, number of elements in A times the number of elements in A times the number of elements in A. Well, there are 2 elements, right, in A. So it's 2 elements, right, times 2 elements times 2 elements. And 2 times 2 times 2 is 8. And you'll notice how many ordered triplets did we have here? You count our triplets, we had 1, 2, 3, 4, 5, 6, 7, 8. So again, the rule here still applies, which is good to know because if you end up with 7 or something, you know that you've miscounted or left one out. If you end up with more than 8, you're like, okay, there must be something repeating here. You can find out which one you've accidentally duplicated. It's just nice to know that you should have exactly 8, right? So that you can confirm you're not missing anything or that you don't have too many, et cetera, et cetera. All right. So another example of this, using 4, 5. So again, it's basically 4, 5 times 4, 5 times 4, 5. So again, order triplet, find all the combinations of 3 that you can. So we're gonna start with this 4. So we'll have 4, 4, 4, 4, 4, 5, 4, 5, 4, and 4, 5, 5, right? Just every combination that we can make out. So 4, 4, 4. So, yep. And then 4, 4, 5, 4, 5, 4, 4, 5, 5. Now I'll do the same thing pretty much with the second part of this, the 5 here. So 5, 4, 4, 5, 4, 5, 5, 5, 4, and finally 5, 5, 5. Again, because of the number of elements in each one is 2, right? 2 elements, 2 elements, 2 elements. We should have a total of 8, right? 2 times 2 times 2 is 8. And you can see we have 8. So that's perfect. All right. Um, these ones are actually little algebra problems, which is, well, they're very simple algebra problems usually. So two order pairs, A and B and X and Y are equal if A is X and B is equal to Y. So like, for example, you can see what we have here. We're told to find the values of X and Y. We have these two, this order pair equals this order pair. So what we should be able to tell from it is that the X portion should be equal to each other and the Y portion should be equal to each other. So in this case, that X plus 1/2 should be equal to that 5/2. And in the other case, we have the Y minus 3 should be equal to the 7. Right? So this should equal that. This should equal that. So all it is just a quick algebra problem for us to solve to try and just solve it for X and Y. So I would subtract 1/2 here. And this is going to give me 4/2. X equals 4/2, which is the same thing as 2. So X equals 2. And then the other one, you can simply just add the 3. And so that's going to be Y is equal to 10. So that's our answers, just 2 and 10. Basically, you're just trying to set up two very simple algebra problems and just solve those. And we're going to do the same thing with um, our following example here. So again, A plus 2 should equal 5. And the B minus 4 should equal 4. So we just solve these two for, the respective A and B's here. So subtract 2, and we see that A is equal to 3. And then on the other side, we'll add 4, and we'll get B is equal to 8. So 3 and 8, pretty simple overall, right? Just again, you just have to know how you're setting it up. And then I think, for the most part, you guys, I think, could solve these equations. So, all right, last couple examples. Suppose we need to code 4 cars, Dodge, Chevy, Ford, Toyota, with the codes SMF. How many different pairs of codes can be generated? So if we're doing cars times codes, then as you'll see, for example, we'll have Dodge S. We'll have Dodge M, and we'll have Dodge, keep spelling it wrong, Dodge F, right? So again, we're going to make all these different pairs. So we have to keep going. We'll have to do Chevy, Ford, and Toyota as well. So Chevy S, Chevy M, and Chevy F. Keep going. We have to do it with Ford, right? So Ford S, Ford M, Ford F, and then finally Toyota S, uh, Toyota M, Toyota F. So each car with each code, and you can see if we count them up, it should be 12. And that's because, of course, the number of cars times the number of codes, in this case was 4 cards by 3 codes, which is 12. And you can see that's how many ordered pairs we created, 12 ordered pairs. So just confirmation there. All right, and then one more time, we'll do this again. And we'll have we'll be done with our Cartesian product of sets. So pizza and code. So we're gonna have, of course, we're doing cheese, pepperoni, sausage, and veggie with S, M, and L. So we'll have cheese S, cheese M, cheese L, etc., etc. Cheese S, cheese M, cheese L, and then pepperoni S, M, and L. Sausage S, M, and L. And then finally, veggie S, M, and L. Don't forget the brackets at the start and end here. And remember, you had 4 pizzas and 3 codes. 4 times 3 is equal to 12. You should have 12 ordered pairs. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. All right. That's gonna do it for Cartesian product of sets. Hopefully it's not too complicated. But if you do have any other questions, you just let me know. I'll see you guys in the next one. Bye for now.